we will be covering Riemann sums and definite integrals in this video. The topics we will be considering: first, we'll try to understand the definition of a Riemann sum, then evaluate a definite integral using geometric formulas, and finally using properties of definite integrals. Let's start with Riemann sums. Riemann sum says if a function is defined on a closed interval a to b, and let delta, or this triangle, be a partition of the closed interval a to b. So this partition basically is like this. You have a, so this is x0, then you have another point x1, x2, and so forth till you hit xn, and that is b. Now here delta xi is the width of the ith subinterval. So suppose there's an xi here and an xi plus 1. So this is delta xi, say. And if ci is any point in this interval, suppose we have a point ci here, then the sum of these, then the sum given by f of ci times delta xi from 1 to n, so basically we're dividing into n subintervals, is called the Riemann sum of f for the partition delta. So in other words, let's look at this graph here. So suppose we have a graph and I have a point, say A to B, and I would like to find the area here. So what do? We divide into some, partition, say x, and this b is xn. So what you're looking at is, it doesn't matter how you want to do it as an over or under. It's just basically you're looking at some point in the interval. You're looking at these, you're adding up all the areas of these rectangles. The best part of the Riemann sums is the function has to be defined on the closed interval, and it says nothing else. There's no restrictions on the function other than it has to be defined on this closed interval. And then on top of it, then these subintervals have unequal widths. You can have a width like this much. This is not the same as this one or this one. So those are certain things we keep in mind. Okay. Now these are the observations that when we're talking of Riemann sums, there's no restriction other than being defined on the interval. It has subintervals of equal width. Then what we do is we look at the largest subinterval and say that is the norm. Norm in simple terms is like the distance here. And if every subinterval is of equal width, then we are back to the things we learned about finding the area under the curve. So each of the width is b minus a over n. But if it is not equal widths, then we look at it b minus a divided by the partition of the highest subinterval less than equal to n. Now remember, as we increase these n's are basically, you can think of these are the rectangles here. As we're increasing the number of rectangles or increasing the number of partitions, then this norm almost becomes very, very small. For us, more important is how do we use it? And we're going to look at it in terms of definite integrals. So what it says is, if my function is defined on a closed interval, then the limit of the Riemann sums over these partitions is given as limit as this norm, which is basically at the highest interval there, approaches 0. That means we're including very, 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 not too many, I would say, rectangles, approaches 0. That means the width becomes very, very, very small. Then we look at the sum of the areas of all these rectangles. That is given by f of ci, that is the length, times the width of the rectangle delta xi. If this happens, then we say f is said to be integrable on the interval, closed interval a to b, and this is how we write it down. So the limit is norm of these partitions approaches 0. That means we have very, very large number of rectangles, then the summation f of ci delta I is nothing but the definite integral from a to b fx dx. This limit is called the definite integrals. This limit has to exist, remember. And the number a is called the lower limit of the integration. The number b is called the upper limit of the integration. We need to look at certain relationships here. The first one, if a function f is continuous on a closed interval, then by default it is integrable on the closed interval. In other words, the integral from a to b, now this is the definite integral, guys, fx dx exists. And how do we represent in terms of area? How do definite integrals look at the area? This is the definition of the theorem, not the definition, but the theorem. If a function f is continuous and non-negative on a closed interval a to b, then the area of the region bounded by the graph of the function, this is the area of the region, guys, we're talking about. Now remember, this is my function fx, and these are where I'm looking at a and b. These are the two ends of the closed and subinterval. So we say the area of the region bounded by the graph of f. This is the graph I'm talking about. I'll try to be nicer so that okay, so this is the graph I'm talking about. The x-axis, it is bounded by the graph of the function above the x-axis and the two vertical lines. So the vertical lines are, guys, here. This one is x equals a, and this one is x equals b, and the area is below the graph of the function and above the x-axis. Okay? Now, first we are going to learn how to find these definite integrals using geometric formulas. So the first thing we're going to do is, we're given this definite integral from 1 to 3, 4 dx. Now let's look at this function. What is my function fx here? This is a constant function. A constant function looks like a horizontal line. The graph of that is a horizontal line, sorry. So this is how my function looks like. We like to find the area of this function between the two integrands, the lower integral. Remember, a is called what? A is called, if you go back, a is called the lower limit and b is called the upper limit between the two limits of the integral. So 1 is the lower limit and the 3 is the upper limit. So we're looking at, so we try to find what the area looks like. So the function is given by a horizontal line, and then you're only looking at the area from 1 to 3. And then we look at, so these are the vertical lines, guys. Okay, not a nicer one. Okay, so you can easily see the picture. I'm kind of really messing it up. Okay, so these are the lines, okay? The two vertical lines. So remember, this line is x equals 1, and this line x equals 3. So what does this area looks like? It looks like a rectangle. So what is the area? Because remember, what's the formula? The function is continuous and non-negative. You already see that. So the area of this definite integral 1 to 3 fx dx is nothing but the area of the rectangle. What's the area of the rectangle? Base into height. What's the base? It's base into height. So base is what? 3. It's not 3. It starts from 1 to 3. So the base is around 2 units. And the height is from, remember, 0 till 4. So the height is 4 units. So the answer is 8 square units. Because it's an area. Okay, so I do not know what the units are, I'm just saying it. Okay, let's look at another example. Now here we are asked to sketch the region corresponding to this definite integral, and then we evaluate using a geometric formula. So the first thing is we look at what is the function given to us. What are the lower and the upper limits? So the a over here, remember, is 0, the lower limit, and the upper limit is 3. And the function which is given to me as is x plus 2. Okay. Now what is this function? It's a linear function with slope 1 and a y-intercept 2. That's where it's given. But we only are looking for the factors between 1 and 2. Clearly, by the theorem we just saw, this function is continuous and non-negative in the closed interval 1 to 3. So that means the integral from a to b fx dx, according to the theorem, I'm just going to show you the theorem once again, guys. This is the theorem I'm talking on slide 7. Okay, that's what we are applying to do these problems. Okay, so this is the area of, it's like a kind of a geometric figure, right? So let's look at the area here. The first thing, it can be divided into 2 parts, right? If you want that way. So it can be the area of this plus the area of this triangle. You can look at it in this form. So if I look at this way, it makes my life more simpler because both of them will give me the combined area. So area of the figure. So what are we going to do? First, we're going to find the area of this plus the area of this. So area of the figure is 1 plus 2. What's the 1? 1 is basically a rectangle. So it's the area of the rectangle plus the area of the triangle. Both of them give us the figure which is here. What's the area of the rectangle? Base, which is 3, height, which is 2. So it's 3 times 2. Plus, what's the area of the triangle? It's half. The base again is what? 3. And what is the height? Remember, it starts from 2 and it's almost hitting here, which is a 5. I'm just looking at the picture here. Okay. But remember, it starts from 0, so I can't write from 5. It is from 2 to 5. So 2 to 5. That means 3 here. Okay. So what do we have? 3 times 2 is 6 plus 9 halves, which is 4.5. So the area is 10.5 square units. One thing, guys, I forgot to tell you is how would we know what are the values? Here we had the nice little picture for us to work with. But suppose if you're not given a picture and you're asked, sketch this region, okay? So I'm going to show you how to sketch the region if the picture is not given. So let's come here. I'm going to show it to you here, guys. So here's the, we're given 0 to x, x plus 2 dx. So when you want to draw the picture of this one, so the first thing you're going to do is you're going to draw your x and y. Okay. Now the next step you're going to do is look at the lower and the upper limits. Mark those points 0 to eyeball them. Now you have to look at what is the value of the function, because you need to know if you want to see what kind of a geometric figure we're going to have. Okay. So what we're going to do is we are going to look at the value of the function when x, the lower limit, is 0. So what's the value of the function? So when x is 0, that's what it means, guys. This is the x, these are the x vertical lines. Remember that. This is x equals 3. Okay. So when x is 0, what is the value of the function? So when x is 0 is what? 2. So that's where my graph will start. Then when my x is 3, that's the upper limit. What is the value of the function when x is 3? 5. So then you go ahead and draw a line, because we know it's a line. And that's what we are given. So this is the graph of you're sketching the graph. And then this is the area, guys, we are looking at. In the questions later on, I might ask you to sketch the region. So this is how you basically sketch the region. And if you're given the sketch, then it's making your life more easy. Okay? Once again, if the sketch is not given, you need to learn how to sketch. And I've shown you all the little steps which will help you work it out. Okay, let's look at one more example. Now this one is a semicircle. It says sketch the region which corresponds to this definite integral here. Then evaluate each integral using a geometric formula. Okay, now here guys, we are given 0 to 3 square root 4 minus x squared. Now this is a semicircle, okay? You're starting from, there's a typo. It should be minus 2, guys, to 2. Minus 2 to 2, no, not 0 to 3, sorry. Minus 2 to 2 square root 4 minus x squared dx. Now, this is the area of a semicircle. Now, what's the area of a circle, guys? We know area of a circle is what? Pi r squared. Semicircle would be half of that. Half pi r squared. What's the radius? That's the radius, guys. Do you notice this one? This is my radius. My radius is 2 units. So what is it? It's half times pi times 2 squared. Oh, sorry. Kind of didn't write this correctly. Okay. It's half pi 2 squared, which is what? Pi 4 over 2, which is 2 pi. Make sure you write down square units. Okay? Now, one more kind of questions which can be asked here is that if you are given the graph and say, set up the definite integral. So what you do is, let's look at this example. So here you'll be given the function. Your main job is, if you're setting up a definite integral, you need to know the limits of integrals. You need the lower limit, the upper limit, and you need to know the function fx dx. Now in these problems, we are already given the function. So what is our job is to figure out what is the lower and what is the upper limit. Now to look at that, what you do is you look on the x-axis, okay? Now when you're looking at the x-axis, where does it start? So it starts from 0 and ends at 2. And that's your lower limit and your upper limit. Okay, let's look at this problem number 18. Fx is 4 over x squared plus 2. Now it's much more easy to write down the function here. Simply copy the function given to you, the lower limit and the upper limit. So clearly by this picture, notice it's from -1 to 1. So that becomes the upper and the lower limit. The lower limit is -1, the upper limit is 1. We always go from left to right. Okay, I can see this picture is not clear, the number 20th picture. So I'm just going to go ahead and basically darken the area. So this is the area under the curve. Okay, so the first thing, it's a function which is already given as a tangent x, and just write dx next to it. Now where does the integral start? It starts at 0, ends at pi4. So it goes from 0, that's the lower limit, and the upper limit, pi4. And I will continue later on the next video regarding the rules and applying those definite integral rules. Thank you.